Example 2.23. An electrical technician requires a capacitance of 2 microfarad in a circuit across a potential difference of 1 kilovolt. A large number of 1 microfarad capacitors are available to him, each of which can withstand a potential difference of not more than 400 volt. Suggest a possible arrangement that requires the minimum number of capacitors. Understand the question. Electrician have large number of capacitors, each one that is with value 1 microfarad. And now he require capacitance in a circuit that is 2 microfarad. And that circuit have the potential difference of 1 kilovolt. It implies that he have to arrange this 1 microfarad capacitors in such a way that the resultant capacitance comes to 2 microfarad, and that particular combination of capacitors which give you the resultant capacitance 2 microfarad can withstand up to 1 kilovolt, means 1000 volt. Now here it is given to you, each capacitor can withstand a potential difference of not more than 400 volt. So first, easily you can understand this thing. If in the circuit 1 kilovolt means 1000 volt potential difference is applied, one capacitor can withstand only up to 400 volt, means minimum 3 capacitors are required in series combination. First of all, clear to all? Because series combination of 3 capacitor will give you the total potential difference that is equal to 1200 volt. And here in the circuit 1000 volt is applied. So now that combination is safe one. So in series, minimum 3 capacitors are required. Okay. But now we want resultant capacitance that is 2 microfarad. So let's think about the parallel combination of this type of 3, 3, 3, 3, 3, 3 are in series. Now, how many rows that we have to prepare of 3, 3, 3, 3 capacitors in parallel? We don't know. So suppose m number of rows, and in each row 3, 3, 3, 3 capacitors are there, are connected in parallel. And in parallel combination, the potential difference across each one, that is same one. So resultant capacitance will be, potential difference will be 1200 volt. So the circuit can withstand for 1000 volt. Now, if in one row you have n capacitors, each with value C, then resultant capacitance of one row, that is C by n. Now, if such m rows are parallel, then C by N plus C by N plus C by N plus C by M, and like M rows are there. So resultant capacitance that we can say C by N into M. But N that is 3 because in one row we connected 3 capacitors. So we can write C by 3 into M, that is equal to 2 because resultant we require 2. Now each capacitor that is with value 1 microfarad. So C is 1. So 1 by 3 into M, that is 2. So M that is equal to 6. Means we have to prepare 6 rows. Now we already discussed in each row there are 3 capacitors in series. So total number of capacitors required, that is 3 into 6 equal to 18. So electrician will take total 18 capacitors, then he will connect 3 capacitor in series, and then after this type of 6 rows prepared and connected in parallel, so requirement will be fulfilled. Clear to all of you now? Example 2.24. What is the area of the plates of a 2 farad parallel plate capacitor given that the separation between the plates is 0.5 centimeter? So capacitance, that is 2 farad, separation between two plate, that is 0.5 centimeter, so that is 0.5 into 10 raised to minus 2. So we can write that is 5 into 10 raised to minus 3 meter. Now we have the equation for the capacitance of parallel plate capacitor, that is C equal to epsilon 0 A by D. We want area of the plates. So make A as a subject. So A that is C D upon epsilon 0. C that is 2. D that is 5 into 10 raised to minus 3. Epsilon 0 that is 8.85 into 10 raised to minus 12. Now solve this one. You will get area of the plates. Clear to all of you? Example 2.25. Obtain the equivalent capacitance of the network in figure. For 300 volt supply, determine the charge and voltage across the each capacitor. Now see here, the circuit given to you, that is with 4 capacitors. So capacitor C1, that is with value 100 picofarad. Capacitor C2 and C3 are with values 200 picofarad. Capacitor C4, that is with 100 picofarad. Supply voltage is 300 volt. We have to find the equivalent capacitance of this combination, means across these two terminals of the battery, the entire combination is given to you. So here first we will calculate the equivalent capacitance, and after that we will think about the charge and potential difference. So at present, just concentrate your mind to calculate the equivalent capacitance. See, let's simplify the circuit step by step. So first of all, here we can say this thing: between the points A and B, these two capacitors C2 and C3 are in series. So resultant capacitance of the series combination of C2 and C3, that is C2 3 equal to C2 C3 upon C2 plus C3, or simply you can write C by 2, that is 200 by 2, so 100 picofarad. So now we can replace these two capacitors C2 and C3 by only one capacitor having capacitance 100 picofarad. Now the equivalent circuit that will be as shown in the figure. Now see this equivalent circuit between A and B, C2 and C3 are removed and only one capacitor C23 is connected. Now you can see this thing across AB, capacitor C1 and C23 are parallel. C1 and C23 are parallel. Now resultant capacitance between A and B, that will be C dash equal to C1 plus C23. C1 is given to you 100 picofarad. C23, that is also we calculated 100 picofarad. So 100 plus 100, so resultant that is 200 picofarad. It implies that now we can replace this combination of C1 and C23 which are parallel by only one capacitor having capacitance C dash equal to 200 picofarad. Clear up to this one? हाँ युग कहीं पूछવું છે તારે બેટા?
ના સર ભૂલમાંથી થઈ ગયું.
Okay. To this one. So for this equivalent circuit in which C dash and C4 are in series, the resultant capacitance of entire network C, that is equal to C dash C4 upon C dash plus C4, that is equal to 200 into 100 upon 200 plus 100. You will get the answer 200 by 3 picofarad. So that is 200 by 3 into 10 raised to minus 12 farad. This is the equivalent, or we can say the resultant capacitance of the given entire network. Clear up to this one? Now we have to calculate charge on each capacitor. Now we know in series combination, charge on each capacitor, that is the same one. So see here, with battery, C dash and C4 are in series. Suppose on C4 the charge is Q4 and on C dash we say the charge is Q dash, but when both the capacitors are in series, Q4 and Q dash are same one, and we can write as per equation Q equal to CV, Q4 equal to Q dash equal to CV. C, that is the resultant or equivalent capacitance of this combination, and that we calculated 200 by 3 into 10 raised to minus 12. Substitute that value here, and V, that is 300. So Q4, that is equal to Q dash, that is 2 into 10 raised to minus 8 coulomb. Clear to all of you up to this? Now we have to switch over to the previous circuit to calculate the charge on C1, C2, C3. Now keep this thing in your mind. The charge on capacitor having capacitance C dash, that is Q dash, that is equal to 2 into 10 raised to minus 8 coulomb. Now see, C dash, that is actual parallel combination of C1 and C2 3. And see here, C1 that is with value 100 picofarad. C2 3 that we calculated, it is also 100 picofarad. So we can say C1 and C2 3 are identical one. Both are in parallel. So total charge Q dash, that will be equally distributed between C1 and C2 3. So now we can write the charge on C1, that is Q1, that is equal to Q dash by 2. Q dash we calculated, that is 2 into 10 raised to minus 8 by 2. So we will get 10 raised to minus 8 coulomb. Similarly, on C2 3 also the same charge, 10 raised to minus 8 coulomb. But now see, C2 3, that is the series combination of C2 and C3. And in series combination on each one, the charge is the same one. So here on C2 3, when charge is Q dash by 2, then we can say the same charge is there on C2 and C3. So we can write now charge on C2, that is Q2, that is equal to charge on C3, that is Q3, and that is equal to this Q dash by 2, and that is 10 raised to minus 8 coulomb. So charges on each capacitor are now calculated. Clear up to this one? Now we have charge on each capacitor and the value of the capacitance for each capacitor, that is given to you. So simply we can calculate the potential difference across each one. Say we have the equation C, that is Q by V, so V, that is Q by C. Now as per that, potential difference across capacitor C1, that is V1 equal to Q1 by C1. Q1 that is 10 raised to minus 8, C1 that is 100 picofarad. So that is 100 into 10 raised to minus 12 farad. So you will get the answer 100 volt. Similarly, potential difference across C2, that is V2 equal to Q2 by C2. Q2 is also 10 raised to minus 8 coulomb. C2 that is 200 into 10 raised to minus 12 farad. Solve this one, you will get the answer 50 volt. Then potential difference across C3, so that is V3 equal to Q3 by C3, that is equal to 10 raised to minus 8 upon 200 into 10 raised to minus 12. Again the same 50 volt. Then potential difference across C4, that is V4 equal to Q4 by C4. Q4 that is 2 into 10 raised to minus 8 upon C4. C4 that is 100 picofarad, so 100 into 10 raised to minus 12 farad. Solve this one, you will get answer 200 volt. So now the problem is completed. Now example 2.26. The plates of a parallel plate capacitor have an area of 90 centimeters square each. and are separated by 2.5 millimeter. The capacitor is charged by connecting it to a 400-volt supply. A. How much electrostatic energy is stored by the capacitor? B. View this energy as stored in the electrostatic field between the plates and obtain the energy per unit volume U. That is nothing but energy density. Hence, arrive at a relation between U and the magnitude of electric field E between the plates. Now see, area of the plates given to you 90 centimeter square. So that is 90 into 10 raised to minus 4 meter square. Separation between two plates, that is 2.5 millimeter, that is 2.5 into 10 raised to minus 3 meter. And it is charged by 400-volt supply. Now first we have to calculate the electrostatic energy stored in the capacitor. So we have the equation for the energy stored in the capacitor, that is half CV square. But see, the capacitance of the capacitor is not given to you directly. So first we have to calculate capacitance by equation epsilon 0 A by D. Area and separation are given to you. So C, that is epsilon 0 A by D. Epsilon 0, that is 8.85 into 10 raised to minus 12. Area, that is 90 into 10 raised to minus 4. Upon separation D, that is 2.5 into 10 raised to minus 3. Solve this one, you will get the capacitance. Now energy stored in the capacitor, that is half CV square. So half, substitute the value of capacitance here which we calculated. V, that is given to you 400, substitute its value and then solve it. You will get the energy stored in the capacitor. Clear to all of you? Now we want to calculate energy density, that is the energy stored per unit volume. So divide this energy calculated, which one is stored in the capacitor, by the volume occupied by the capacitor. So energy density small u, that is energy stored in the capacitor capital U upon volume, that is area into distance d between two plates. Now substitute the value of energy which we calculated here in this equation. Area given to you for the plates, that is 90 into 10 raised to minus 4, and the separation between the plates, that is given to you 2.5 into 10 raised to minus 3. Solve this one, you will get energy density. Okay. Now here it is given to you, arrive at the relation between U and the magnitude of electric field E. Now see, U, that is half CV square. C, that is epsilon 0 A by D into V square. But V, that is E into D. So we can write half epsilon 0 A by D into ED whole square. So half epsilon 0. Now here this D square upon D will give you D. So we can write half epsilon 0 A into D into E square. But AD, that is volume, take it on left hand side. So U upon AD, that is the energy density. So here on right hand side you will get half epsilon 0 E square. Clear? So this is the energy density in terms of the magnitude of electric field. Clear to all of you? Example 2.27. A 4 microfarad capacitor is charged by a 200 volt supply. It is then disconnected from the supply and is connected to another uncharged 2 microfarad capacitor. How much electrostatic energy of the first capacitor is lost in the form of heat and electromagnetic radiation? This type of problems we already discussed. See, first case, 4 microfarad capacitor is charged by a 200 volt supply. So 4 microfarad capacitor connected with 200 volt supply. So energy stored in the capacitor. Say it is initial energy. So we can write Ui, that is half C1 V square. So Ui, that is half C1, that is 4 microfarad. So that is 4 into 10 raised to minus 6 farad. V, that is 200 volt. So 2 into 10 raised to 2 square of 8. And you will get the answer 8 into 10 raised to minus 2 joule. Okay. Now calculate charge deposited on the capacitor also. So charge on the capacitor, that is C1 into V, 4 into 10 raised to minus 6 into 200. So you will get 8 into 10 raised to minus 4 coulomb. Now this first capacitor is disconnected from the battery and connected to uncharged capacitor having capacitance 2 microfarad. So second situation, C1 4 microfarad connected with C2 2 microfarad. Initially C2 was uncharged, C1 is charged, and charge on C1, that is Q. So we can say the total Q amount of charge is there in this circuit. Which one is now distributed between C1 and C2? Suppose when the common potential is established, the charge on C1, that is Q1, and charge on C2, that is Q2. So we can write Q1, that is equal to C1 upon C1 plus C2 into Q. C1, that is 4 into 10 raised to minus 6, and C1 plus C2, that we can write 4 plus 6 microfarad, so that is 6 into 10 raised to minus 6. Total amount of charge Q, which one is distributed between those two capacitors, that is 8 into 10 raised to minus 4. You will get Q1, that is 16 by 3 into 10 raised to minus 4 coulomb. Similarly, we can calculate Q2, that is equal to C2 upon C1 plus C2 into Q. C2, that is 2 microfarad, so 2 into 10 raised to minus 6 farad. C1 plus C2, that is 4 plus 2, 6 microfarad, so that is 6 into 10 raised to minus 6. Q, 8 into 10 raised to minus 4. So you will get Q2, that is 8 by 3 into 10 raised to minus 4 coulomb. Clear up to this one? Now energy stored in capacitor C1, U1 dash, that is equal to Q1 square upon 2C1. Q1 we calculated 16 by 3 into 10 raised to minus 4, take square of it, upon 2 C1, that is 4 into 10 raised to minus 6. Solve this one, you will get energy stored in capacitor C1. Then energy stored in capacitor C2. So U2 dash, that is equal to Q2 square upon 2C2. Q2 we calculated 8 by 3 into 10 raised to minus 4 and take square of it upon 2C2. So 2C2, that is 2 into 10 raised to minus 6. Solve this one. You will get U2 dash, the energy stored in second capacitor. So the total energy of the system, that is U1 dash plus U2 dash, take the summation of these two and calculate the final energy stored in this system. Now loss of energy, that is initial energy minus final energy, and you will get the loss of energy in the form of heat and electromagnetic radiation. Clear to all of you? Example 2.28. Show that the force on each plate of parallel plate capacitor has a magnitude equal to half QE, where Q is the charge on the capacitor and E is the magnitude of electric field between the plates. Explain the origin, the factor cube 1 by 2. Now, electric field of any charged plate, that is given by the equation sigma upon 2 epsilon 0. In chapter 1 we derived this thing. Now when another plate is placed against first one, then we can say that second charged plate is in the electric field of first one, and there is charge Q. So the force on the second plate, that we can write Q into E1, Q that is sigma into A. So we can write the force, that is sigma into A into E1. So that is equal to sigma A. Now E1, that is sigma upon 2 epsilon 0. So resultantly we can write sigma square A upon 2 epsilon 0. So here substitute sigma, that is Q by A. So we can write sigma square, that is Q square upon A square into A upon 2 epsilon 0. 1 A is cancelled. So we'll get Q square upon 2 epsilon 0 A. Now divide numerator and denominator both by D. So Q square by D upon 2 epsilon 0 A by D. But this epsilon 0 A by D, that is C. So you will get Q square upon 2DC. Now Q square upon 2DC is replaced by Q by V. So 1 Q is cancelled. Take this V in numerator. So half into Q into V by D. But V by D, that is electric field E. So resultantly our equation, that is half into Q into E. Clear up to this one? Say, when the capacitor is charged at that time, the charge on the capacitor increases from 0 to Q. And therefore, the electric field established between two plates of the capacitor, that also increases from 0 to E. And therefore, the average value of the electric field E by 2 contribute in the force. And therefore, this factor 1 by 2 appears here. Clear to all of you? Now example 2.29. A spherical capacitor consists of two concentric spherical conductors held in position by suitable insulating support. Show that the capacitance of the spherical capacitor is given by C equal to 4 pi epsilon 0 R1 R2 upon R1 minus R2, where R1 and R2 are the radii of outer and inner spheres respectively. Okay. Now see, two spherical shells, inner one that is with radius R1, outer one that is with radius R2. Question માં R1 R2 કરતા આપણે અહીંયા અલગ લીધેલી છે. ક્વેશ્ચન માં ઇનર ને R2 કહી છે ને આઉટર ને R1 કહ્યું છે. મારાથી ભૂલથી અહીંયા ઇનર ને R1 અને આઉટર ને R2 લેવાયું છે, but it doesn't make any difference to the result. Okay. Now charge on the outer cell that is plus Q, charge on inner cell that is minus Q, and the electric field that is from outer to inner. Now we want to derive the equation for the capacitance of this spherical capacitor. So we have to find the potential difference between these two conductors, means these two plates. So we can write V that is equal to minus integration R1 to R2 E dot dr. So we can write minus integration R1 to R2 E dr cos theta. So from R1 to R2 your dr that is inner to outer, field that is outer to inner, means angle between E and dr that is pi. So we can write now V that is equal to integration R1 to R2 E dr. Electric field that we can give by kq upon r square. So integration R1 to R2 kq upon r square dr. Kq that is constant one. So integration of 1 upon r square that is minus 1 upon r. Limits R1 to R2. Kq. First substitute r equal to R2 upper limit, then minus r equal to R1 the lower limit. So we can write V that is equal to Kq into 1 upon R1 minus 1 upon R2. Now, as per definition, capacitance that is Q by V. So from this equation, derive the equation for Q by V. Now see, K is replaced by 1 upon 4 pi epsilon 0. Q, here take R1 R2 LCM, so R2 minus R1 upon R1 R2. So resultantly we can write Q by V that is equal to 4 pi epsilon 0 into R1 R2 upon R2 minus R1. So finally we will get the capacitance C that is Q by V equal to 4 pi epsilon 0 into R1 R2 upon R2 minus R1. So here you will get the difference of outer radii and inner radii. Whatever is the notation is taken for that. Clear to all of you? Example 2.30. A spherical capacitor has an inner sphere of radius 12 centimeter and an outer sphere of radius 13 centimeter. The outer sphere is earth and the inner sphere is given a charge of 2.5 microcoulomb. The space between the concentric spheres is filled with a liquid of dielectric constant 32. Then A. Determine the capacitance of the capacitor. B. What is the potential of the inner sphere? C. Compare the capacitance of this capacitor with that of an isolated sphere of radius 12 centimeter. Okay, and why the latter is much smaller. Now this one is the case of spherical capacitor, and we already derived the equation for the capacitance of spherical capacitor. See here, inner radii, that is 12 centimeter, so that is 12 into 10 raised to minus 2 meter. Outer radii, that is 13 centimeter, that is 13 into 10 raised to minus 2 meter. Q, that is 2.5 microcoulomb, so that is 2.5 into 10 raised to minus 6 coulomb. And dielectric constant of the liquid, that is 32. Now see, we know this thing when the material having dielectric constant K is introduced between two plates of the capacitor, the capacitance becomes K times. So here also the same thing happens. We have the capacitance for spherical capacitor, that is 4 pi epsilon 0 into R1 R2 upon R2 minus R1. But now between these two spherical cells, a liquid of dielectric constant K is introduced. So capacitance becomes K times. So it is multiplied by K. Now substitute all the values. K 32, 4 pi, that is 3.14, epsilon 0 8.85 10 raised to minus 12, R1 R2 12 into 10 raised to minus 2, 13 into 10 raised to minus 2. So you will get 12 into 13 into 10 raised to minus 4. Then R2 minus R1. So 13 into 10 raised to minus 2 minus 12 into 10 raised to minus 2. So resultantly you can write 13 minus 12 into 10 raised to minus 2. Solve this one, you will get the capacitance of this capacitor. Clear up to this one? Now we have to find potential of the inner sphere. So charge on the sphere, that is Q, radius, that is R1. So potential, that is equal to KQ upon R1. K, that is 9 into 10 raised to 9. Q, that is 2.5 into 10 raised to minus 6 upon R1, that is 12 into 10 raised to minus 2. Solve this one, you will get the potential on the inner one. Now we have the potential for the inner one, that is KQ upon R1. K, that is 1 upon 4 pi epsilon 0 into Q by R1. So from this equation, if we write Q by V, then that is the capacitance of that isolated sphere, that is 4 pi epsilon 0 R1. So C dash, that is 4 pi epsilon 0 8.8 5 into 10 raised to minus 12, 12 into 10 raised to minus 2, that is R1. Solve this one, you will get the answer. Clear to all of you? Example 2.31. Answer carefully. A. Two large conducting spheres carrying charges Q1 and Q2 are brought close to each other. Is the magnitude of electrostatic force between them exactly given by Q1 Q2 upon 4 pi epsilon 0 R square, where R is the distance between their centers. Here we can't say the force that is exactly equal to Q1 Q2 upon 4 pi epsilon 0 R square, because when two spheres are taken close to each other, then the distribution of charge that becomes non-uniform one. The charge on the spheres will not behave like a point charge concentrated at the centers. Clear to all of you? B. If Coulomb's law involved 1 upon r cube dependence instead of 1 upon r square, would Gauss's law be still true? No. Simple thing. Gauss's law is derived as per the inverse square law. So it will not be true. C. A small test charge is released at rest at a point in an electrostatic field configuration. Will it travel along the field line passing through that point? Not necessarily. Field line that give the direction of acceleration, not of velocity. Because the field line that will give you the direction of electric field at a particular point. And electric field, that is nothing but the force acting on unit positive charge. So if any test charge Q is at that point, then force on it, that is QE, and force F equal to MA. Means we can say at a point when test charge is there on the electric field line, then it will give you the direction of acceleration of that particular charge, not of velocity. So here we can't say it will travel along the field line. Clear to all of you? D. What is the work done by the field of the nucleus in a complete circular orbit of the electron? What if the orbit is elliptical? So work done will be zero, because work done that does not depends on the path, it depends only on the initial and final position. So when circular orbit or elliptical orbit, when electron complete the revolution, their initial and final position, that is the same one. So potential difference between these two positions, that will be zero. So work done, that is equal to zero. Clear? Next, E. We know that electric field is discontinuous across the surface of a charged conductor. Is electric potential also discontinuous there? No. Potential remains continuous, because potential, that is the scalar quantity. Clear? F. What meaning would you give to the capacitance of a single conductor? So for that we can imagine the second conductor, that is at infinity. Clear? Next, G. Guess a possible reason why water has a much larger dielectric constant, that is equal to 80. Then say mica, that is equal to 6. Because water molecules have strong permanent dipole moment. Therefore, its dielectric constant, that is large one. Clear? Next, example 2.32. A cylindrical capacitor has two coaxial cylinders of length 15 centimeter and radii 1.5 centimeter and 1.4 centimeter. The outer cylinder is earth and the inner cylinder is given a charge of 3.5 microcoulomb. Determine the capacitance of the system and the potential of the inner cylinder. Neglect and effects. It implies bending of field lines at the ends. So see here, the cylindrical capacitor is given to you, and for cylindrical capacitor, we already derived the equation for the capacitance that directly we can use here. See, B, the outer radii, that is 1.5 centimeter, that is 1.5 into 10 raised to minus 2 meter. Inner radii, that is 1.4 centimeter, that is 1.4 into 10 raised to minus 2 meter for this given two coaxial cylinders which form the cylindrical capacitor. The length of the cylinder, that is 15 into 10 raised to minus 2 meter. Okay. Now charge given to the capacitor, that is 3.5 microcoulomb. So that is 3.5 into 10 raised to minus 6 coulomb. We have the equation for the capacitance of cylindrical capacitor, that is C equal to 2 pi epsilon 0 L upon ln B by A. Substitute the values. So C equal to 2 pi 3.14 epsilon 0 8.85 into 10 raised to minus 12 L, that is 15 into 10 raised to minus 2. Now ln is converted into simple log. So 2.303 log 1.5 upon 1.4. Now solve this one. You will get the capacitance of this given cylindrical capacitor. Clear? Then the potential V, that is Q by C, Q that is 3.5 microcoulomb. So 3.5 into 10 raised to minus 6 upon capacitance C, which we calculated here. Substitute its value, you will get the potential. Example 2.33. A parallel plate capacitor is to be designed with a voltage rating 1 kilovolt using a material of dielectric constant 3 and dielectric strength about 10 raised to 7 volt per meter. Dielectric strength is the maximum electric field a material can tolerate without breakdown. It implies without starting to conduct electricity through partial ionization. For safety, we should like the field never to exceed, say, 10% of the dielectric strength. Then what minimum area of the plates is required to have the capacitance of 50 picofarad? Now see, the voltage rating, that is 1 kilovolt, means 1 into 10 raised to 3 volt. It implies that this capacitor should withstand up to 1 kilovolt. Then the material with dielectric constant K is used here. So K, that is 3, and its dielectric strength, that is given to you 10 raised to 7 volt per meter. Capacitance that we require, that is 50 picofarad. So 50 into 10 raised to minus 12 farad. And now here it is given to you, for safety, we have to take the electric field, that is 10% of its dielectric strength. So electric field that we have to take 10% of E dash. So that is 10 by 100 into 10 raised to 7. So that is 10 raised to 6 volt per meter. This much data is given to you. Clear up to this one? Now, Capacitance C, that is K epsilon 0 A by D. So area A of the plates, that is equal to CD upon K epsilon 0. Now electric field E between two plates of the capacitor, that is given by E equal to V by D. So here there is no information about D, so replace D by V upon E. V, that is given to you, yes, 10 raised to 3. And E, here we calculated 10% of the dielectric strength, 10 raised to 6. So D comes to 10 raised to minus 3 meter. Now substitute the values. So A, that is C, 50 into 10 raised to minus 12, D 10 raised to minus 3, K 3 epsilon 0 8.85 into 10 raised to minus 12. Solve this one, you will get the area of the plates required. Clear?